Jai Hind, welcome to class of communications. We are studying angle modulation in analog and digital communication, and in the previous lecture we have covered how we can generate frequency modulated wave, right? Just a quick revision of what we have studied so far. We know that in angle modulation we modulate a continuous wave, right? So this is a kind of analog modulation where message is also continuous in nature and carrier is also a high frequency continuous wave. Here the high frequency carrier is altered with respect to the instantaneous value of the message signal, and the parameter which we deal with for alteration is the angle of the wave, right? As we all know that our basic normal sine wave, a pure sinusoid, can be represented as a pure sinusoid can be represented as a sine omega t. So what are the parameters of a wave that we can actually alter if we want to perform modulation is the amplitude or the angle, right? So when we alter the amplitude of a high frequency carrier wave with respect to instantaneous value of a message signal, that kind of modulation is called as amplitude modulation, and if we alter the angle of the wave, that kind of modulation is called as angle modulation. And within this angle there are two factors, like if I expand this omega, I get to see this is 2 pi f, right? Frequency term is there, and this complete is called as the phase angle, and if there is some deviation in the phase angle, that is represented by plus minus phi t, and this complete is my theta t, that is the phase angle. So with an angle modulation, my frequency and phase modulation comes. So in this unit we have been studying about angle modulation so far, its definition, the expression, how waveforms can be altered, and how the modulation takes place, and how then we studied about narrowband and wideband FM. After that we have seen techniques of generation of frequency modulated wave. So in today's lecture we are going to cover frequency FM wave demodulation. If I do use frequency modulation technique, then for demodulation what are the ways which I can use, right? There are two ways or two methods for demodulation of my FM wave, which are called as frequency discrimination method and phase discrimination method. We'll take each one of these techniques one by one, right? First of all, let me once again draw the waveform for a frequency modulated wave, which will help us out to do frequency modulation, right? As we're talking about analog communication, so my message signal is a continuous wave, right? The kind of carrier which we are using is a high frequency wave, high frequency continuous wave, right? If I talk about FM, then the frequency of this high frequency carrier waves will further be changed with respect to the instantaneous value of the message signal, and my message signal here is a voltage signal. So as the voltage changes, like when it rises the frequency will increase, and when it falls the frequency will decrease. So I'll draw the markings, and this will be the point where frequency will be maximum, and this will be the point where frequency will be minimum. And we have to take care of one thing, that this change will be gradual, right, as this is a continuous wave modulation. So this frequency will keep increasing, and this will be the point where frequency is maximum, and again it starts falling, and this will be the point where frequency is minimum, and again it will start rising, right? So this is how I will get my frequency modulated wave. Now for demodulation, I usually represent my message by MT or XT, carrier by CT, and modulated wave by ST. It's better to write FM in subscript so that it clearly depicts that the modulation technique which I'm using is frequency modulation. At the time of demodulation, I have to go back from here to here. That means I need to have a circuit that should be able to read the frequency variations, and it must be able to convert those frequency variations into uh, uh, amplitude or voltage variations. So I need such kind of circuitry. So there are two common methods for conversion of such uh, form of modulation into actual audio signal, which is called as frequency discrimination and phase discrimination method. Let's see each one of it. We know that equation of FM can be represented as ST, modulated waveform is AC cos 2 pi FCT plus 2 pi KF integration of MT with respect to T, right? Here I know AC is the carrier amplitude, FC is the carrier frequency, right? And this is the frequency sensitivity, right? So and this depends on integration of the message. This part we have already covered in the first lecture. Now when I to remove it, when I differentiate the above equation with respect to T, what do I get? When d by dt of st, when I do d by dt of st, after differentiation I get this term minus of AC 2 pi fct plus 2 pi kf mt sine of 2 pi fct plus 2 pi kf and integration of mt dt. This is after differentiating this equation. Now as I can write minus sine theta as sine theta minus 180 degree, using this in this equation I can rewrite d by dt of st as AC 2 pi fc plus 2 pi kf mt sine 2 pi fct plus 2 pi kf mt dt, and sorry, this is 180 degree, right? So a rate of change of this modulated signal with respect to time can be rewritten in this form, right? I can rewrite my equation like this. So what basically happens in frequency discrimination method, in those previous equations, the amplitude term resembles the envelope of AM wave and the angle term resembles the FM wave. Here, what is our requirement? Our motive is that modulating signal, we need to retrieve back our MT, right? Hence, we can recover it from the envelope of AM wave, and the following and in the next slide I'll show you a figure that shows the block diagram of FM demodulation using frequency discrimination method. We have checked that how my modulated signal changes with time. Now if I need to retrieve back my voltage variations from these frequency variations, what kind of circuit I can use? The first method, using frequency discrimination, what we can do is we can first of all convert my frequency variations into amplitude variations. Once I am able to successfully implement and convert my frequency variations into amplitude variations, in the next step I may use an envelope detector that will read the envelope value and will be able to plot back my message signal, right? So this gives me an idea that let's first convert frequency variations into amplitude variations and then read the peak values of the envelope, and you may detect your original signal back. So what we initially use is a differentiator, right? And then we may use an envelope detector, and this will demodulate my output wave. Here this block diagram consists of differentiator and an envelope detector, and this differentiator here is used to convert the FM wave into a combination of AM wave and FM wave. Here there are variations of the frequency within, but corresponding to that it will make the amplitude variations to occur as well. This means it converts the frequency variations of FM wave into corresponding voltage variations. We know that operation of envelope, we know that how my envelope detector operates. What it will do, it will read the peak values of the amplitude and will retrieve back the message signal. If we are able to successfully plot amplitude variations corresponding to frequency variations, because what happened initially what happened, corresponding to amplitude variations there were frequency variations. Now if your circuit is intelligent enough to convert these into amplitude variations, now reading those peak values, we can detect back our signal. Then it produces the demodulated output of AM wave, which is nothing but the modulating signal. What is my modulating signal? My message signal, my MT, or at times it is represented as XT. It is the message signal, modulating signal, or the intelligence, right, or the information signal. Another method is, as we know that angle consists of frequency and some phase variations, right? The complete angle, if I vary the frequency content only, then the complete angle also changes, right? From the wave equation, you know, AC equals to A sine omega t. When I have AC equals to A sine omega t, when I vary the frequency part, we know that omega equals to 2 pi. When I vary the frequency part only, the complete angle also changes, right? So instead of focusing on frequency variations, let's read the complete phase variations, and corresponding to the phase variations, let's retrieve back our amplitude variations, that is voltage signal or the modulating signal. So phase discrimination method exploits this property of my modulated signal, that it reads the phase variations and try to retrieve back the message signal from these phase variations. So this kind of setup we need. Input to my demodulator will be my FM wave, which is represented as ST. It will go to a multiplier, or we may call it as product modulator as well. Another input to it will be a voltage controlled oscillator output, that is some signal, right? And how this operates, we'll study about it. The output goes to low pass filter, as we are talking of the demodulation. So of course it will be low pass filtered and we get demodulated signal. Now how this voltage control oscillator works, corresponding to the input signal, corresponding to the input voltage value, it will generate certain frequency. This is how my VCO works, right? It will not generate a fixed frequency. This is an oscillator, of course it will be generating some frequencies, but the frequency that it generates is not a fixed frequency. According to the input voltage, its frequency varies. And when this frequency and this frequency, they pass through the multiplier, there are multiple harmonics that you're going to get here, which will represent the final output as PT. But out of those harmonics, my low pass filter will tend to pass the frequency which is close to my message frequency or modulating frequency, and hence I'll be able to retrieve back my demodulated signal, right? It consists of a multiplier, product modulator, the low pass filter, and VCO, voltage control oscillator. Here VCO produces an output signal VT whose frequency is proportional to the input signal voltage DT, right? Initially, when the signal DT is 0, it adjusts the VCO to produce an output signal VT having a carrier frequency at minus 90-degree phase shift with respect to the carrier signal, right? So here my FM wave ST and the VCO output VT are applied as inputs of the multiplier, and this multiplier or product modulator will produce the output having a high frequency component and a low frequency component, right? And passing it through a low pass filter will of course pass the frequencies which lie in the low range, right, which are close to the message frequency. The filter will eliminate the higher frequency component and produces only the low frequency component as its output. Now this low frequency component contains only the term related phase difference, hence we get the modulating signal MT from this output of the low pass filter, right? So I hope the working is clear from here, right? This is how my phase discriminator method works. Now there is one more kind of demodulation that we, depending on the phase variations, we may use a PLL circuit for frequency demodulation, like FM wave demodulation. What is a phase lock loop? We all are aware with the basic working of a PLL. It locks the phase and the circuit works in such a way that we get the desired result here. Here, to the phase detector, we do not directly give the frequency modulated wave, but it is passed through, like the complete receiver will have a setup of radio frequency receiver. The radio frequency receiver, the first block will be your the antenna which will be receiving the radio frequencies, right? Radio frequencies are first converted into intermediate frequencies and then finally demodulation takes place. So here to the phase detector we give an input which is in the output of the IF stage, right? So input from IF stage is provided here. It goes to the phase detector. To the phase detector, another input that goes is through VCO, voltage control oscillator, right? So it will give a certain frequency that this VCO is generating, and in the loop we have a, and for the feedback we have a loop filter, right? Loop filter and amplifiers, they help me demodulate it. Let's give it a read how it works. Here the PLL demodulator takes the condition where no modulation is applied at the carrier, is in the center position of the passband. True. Suppose we are giving solely the carrier where no modulation takes place, then it is at the center position, right? Position of the passband. The voltage on the tune line to the VCO is set to the mid position, true. So it is not varying and it is not producing any other frequencies. However, if the carrier deviates in frequency, that is the case. If it is a frequency modulated wave, the actual frequency deviates from the carrier. We know that how much deviation is represented as del f, and the central frequency carrier from the carrier, it deviates in both the direction with del value, right? So if the carrier frequency is called a central frequency and it reaches somewhat higher value and somewhat lower value than the carrier frequency, that it oscillates around the carrier frequency, which is true. So if the carrier deviates in frequency, then the loop will try to keep the loop in lock. For this purpose, it is called as PLL. For this to happen, now the VCO frequency, voltage control oscillator frequency, must follow the incoming signal, and in turn for this to occur, the tune line voltage must vary. If it wants to keep the loop in lock, then VCO output must vary, right? We can see it from the diagram. If I want to keep it in lock, this must vary. If it was FC only, it is in idle condition, it is working. But if it varies from FC towards F max or towards F min, which is the practical case of FM modulated wave, then to keep it in lock, the VCO will, the output of VCO will vary. Now monitoring the tune line shows that the variations in voltage correspond to the modulation applied to the signal. And now if you closely watch the tune line, you'll observe that how much variations you are observing in the output voltage. It is corresponding to the modulation applied to the signal, that is frequency variation. It is corresponding to the frequency variation. By amplifying the variations in voltage on the tune line, it is possible to generate the demodulated signal. This is how my basic PLL works here for FM demodulation. So this is all about the type of frequency demodulators that we use for FM wave demodulation, right? So we discussed about frequency discrimination method and phase discrimination method. These are the block diagrams of frequency discrimination, phase discrimination, and separately we have discussed about PLL as well. That's it for today. Thank you.